students. Welcome to Module 15. Now in 15 we talk about distribution of sample proportions. What does that mean? When we get a sample with some categorical data, we can determine what proportion of the sample answered yes or no or chose a particular option. That becomes our sample proportion. However, if we were to take a different sample, then we might get slightly different answers. So this section explores what happens when we take a bunch of those samples and try to see what kind of distribution we get. And then we can start to understand how one sample might fit into that distribution and help us to think about whether it would be rare or unlikely to see a sample of this size. All right, let's take a look at an example first off. I think it's good to do a little bit of simulation first. So this is an applet from Rossman Chance, and I'll put this as a link on the technology resource page. This allows you to do some proportions, and we can choose to use either coins or spinners. I'm going to go ahead and use spinners. We're going to do it 7 times to represent the 7 cards that we drew. I'm just going to do it once here to get a feel for it. So now when it says heads, we're going to assume that heads is like success. So in this sample of 7, we had, let's say, 5 black cards and 2 red cards. Okay, so that gives us down here a proportion for our sample of 71%. Okay. Now remember, this sample has multiple data points. However, when we turn that into a single number to represent the sample, we call that number a statistic. So statistics relate to our sample, parameters relate to the population. So up here on top where it says probability of heads, that would be a population proportion, also known as a population parameter. Okay, so that was one sample. Now again, if we ran that sample, that's great, 71%. But let's do it again and just kind of see how likely that was. Here we go. This time, it was 4 and 3 this time. Okay, so one more little dot shows up down here, about 57%. Okay. So now this time I'm going to run 3 samples, and it's only going to show me the last one, the last result. And what happened is I got one down here at 43, and I got one more at 71%. I'm going to do 5 more. This will give us a total of 10 samples. And what you can start to see is there is some distribution of the samples. They definitely seem very clustered in here. So why don't I do another 10 samples just to see how it begins. Look, oh, now there's more at the 43 and a few down at 29, even one up at 86. That's possible. So I'm going to click Draw Samples, and what it's going to do is it's going to continue drawing 10 samples at a time. You can watch right here, my total is now 50. And what I want you to notice is what begins happening to the distribution. The distribution begins taking on kind of a bell shape, a normal distribution. And if I jump up and start doing 100 repetitions at a time, you'll start to see that it really does take on that normal shape, if you will. Really symmetrical. And so if I click here in a normal approximation, I can see what the normal curve looks like there. It's very close. A really nice representation. All right, so but what does this tell us then? Is it possible that we would see something where we would get all 7 cards being black? And you can see over here there is a little tick mark there. So we could look and say, we could say as extreme as, let's say, 90%. And what you'll notice is it actually puts a bar in here. And it says, how often does that happen? And it says, in the 900 samples that have been run so far, it has happened 0.0056, which is less than 1% of the time. So yeah, I would consider that to be pretty doggone rare. You could switch this and say, let's go a little bit lower. Let's say maybe 84%. And now you'll see that the chance that we get in it kind of one of these very extreme values is about 5%, a little bit over 5% in our sample. Okay. Now if you come down here and click the normal approximation allows you to see the theoretical value. And it says even though you saw about 5% in your groupings, you should end up at about 0.036 using a z number of 1.80. So that's what we'd be using to get this value. If we went back up and said, well, what about, getting 90% or higher? Well, now we're at a z-score of 2.12, which is more than 2 standard deviations above the mean, and that's why almost everything is below that value, and we get a p-value, which is a probability, should happen about 1% of the time that we get above that number. And if you decide to put in 100% right off the bat, you can put that in as well, and just say, let's get 100% exactly, and you can say, well, that's a z-value of 2.65, that's even higher, and we should get a value about 0.0041. This is the theoretical down at the bottom, and our value was about 0.0056 that we observed in our samples, and that's pretty darn close. So again, what happens? As I take more and more samples, I begin to see that the samples form a distribution. This is known as a sampling distribution. So each one of the little tiny dots in here represents a sample of 7. So now you're going to see something that's pretty cool that happens is if, I'm going to turn off animate because I don't need to animate, and I'm going to hide the spinners. I don't really need to see the spinners working here. But let's take that 50%, and this time we're going to do 20 tosses or 20 draws of a card. And let's go ahead and see what happens now. So again, I can do this about 900 times, and I'll get that distribution. But what I do want you to notice is now there's nothing higher on the top end, because now we have to do 20 tosses in a row, and 20 tosses are 20 draws out of the deck. The chances of you getting all 20 being black is now, at least in our sample, incredibly, well, it didn't happen. It happened 0 times. Okay, so out of 20, we could say, well, let's say we got 2 of them that were black. Did that ever happen? And we would say 2 of them that are black, that never happened either. In theory, it would happen about 2 times out of every 10,000 draws. So that would be very, very rare. So what we're beginning to see is that the number of times that you toss, it actually begins changing the standard deviation, which is how spread out things are. Let me repeat that one more time. This time I'm going to do 50 tosses. I want you to see what happens if I do 50 tosses and I draw here. Take a look at that standard deviation that we're seeing. The standard deviation here with 50 tosses is about 0.07. And if I do this with 20 tosses, it looks like the standard deviation is about 0.11. The mean in each of those seems to be right around 0.5, which makes sense. We would want that to happen, and it should happen that if our population is about 50%, that we are drawing about 50%. All right, let's take a look at how this is going to impact us as we go through. You're going to see a little bit of an applet where you get a chance to run with different percentages and different n values. So you get a chance to see how unlikely something is. And again, what we're going to see is when you find that standard deviation, the standard deviation away from the mean creates those little brackets of 1 standard deviation or 2 standard deviations above the mean or below the mean. And so you can run samples here, and it's very similar to the applet that I gave you. And what I hope you can see is that the standard deviation with 50 is very different than the standard deviation with 20, or the standard deviation with 10. If you went all the way down to 10, the standard deviation is much higher. There's a lot more variability in those sampling distribution. So you'll explore that a little bit with an applet on a couple quizzes. And the idea that we're looking at, let me grab my drawing tablet here. The idea we're looking at is that there are really a few pieces we have to be aware of. So please be aware of these as you are running through. First, you want to make sure that you are aware of the distribution has to have a center. And so the mean is the population proportion. We're going to use P for that. The spread is how distributed things are, how much variability there is. And the standard deviation of the sampling distribution is also called the standard error, so you're going to see that. But that comes from the population proportion and the fact on the bottom here. So when you look at it, it's the square root of p times 1 minus p. So p is your chance of success, and 1 minus p is the chance of not having success. And then you divide by n. So again, if you're dividing by n, that's going to make that value smaller. If you divide by a larger number, your value gets smaller. So you are decreasing variability when you increase the number of data points in your sample. Okay, so again, this is for your population, and I'll put that in parentheses here, population. There will be a different symbol. You're going to see a p with a little hat on top of it, and that's going to be for your sample. Okay, so we do call that p hat, and that's just our way of saying it's still a proportion, but it's not the one for the population. So we have to make a little bit of a change in our symbols. And lastly, the most important piece is in order for us to be able to use the normal model, we have to have a little bit of a test to see if it's a good fit. And that good fit comes up when we need about 10 successes and 10 failures to happen. So what we're going to check is you're going to multiply the number of data points in your sample times the probability that it happens. And you're going to do the same thing, number of things in your sample multiplied by the probability it doesn't happen. Both of those have to be 10 or more. If you go on in statistics, you might see other classes where they say it needs to be 20 or more. That's where they want even more of that convincing evidence that they should be using this model. And some other classes might be okay if you only had 5 successes and 5 failures. But we're going to use 10 as our number. So, as we take a look, let's go through and do an example. I'm going to jump over to Desmos here. Okay, and I'm going to refresh this. So, what I would do first is with our sample that we had a p-value of 50%. Okay. We have our standard deviation we need to calculate. So standard deviation would be the square root of 50% times 1 minus 50%, which would be 50%. And we're going to divide by 7 because we only had 7 in the sample. So now I'm going to jump down here and put that in. Let's see here. I'm going to put the square root, then I'll put the fraction button, and then I can put in 0.5 times 0.5 on top. I'll put my 7 on the bottom, and I end up with a standard deviation of about 0.1889. You know, for what we're doing, why don't we just kind of say that that's approximately 0.19. Okay. So what do we have? We have then a distribution that has a mean of 50%. And the standard deviation is 0.19, so that means if I go up 1 standard deviation, I would be at 0.69, and if I go down 1 standard deviation, I'd be at 0.31. Right? So I'm going up and down 0.19, and then if I did it one more time, I'd be up even higher. Going up 1 more standard deviation would be 0.7, 0.88, it looks like there. And going down another would put me at 0.12. All right, so nice and symmetric. Now, remember, we ended up with our sample, if you remember when we were drawing, we ended up with a value of, right up here. Our value was 100%, so 1.00. So what we would need to do is we would need to take our p hat, which is 1.00. That's what we observed in our sample, and we would need to calculate the z-score. So let's do that together. So the z-score would be my p hat, which is 1, minus the mean value for the distribution. In this case, that's the population proportion. Okay, and I would divide by 0.19. So let's see what we come up with. Subtraction gives us 0.50 divided by 0.19, and I'm going to jump over here to Desmos and see what we end up with. And I need 0.5 divided by 0.19, and it says 2.63. Perfect. So this means I have a z-score of about 2.63. Okay, well, then that means that what we observed was pretty rare, but how rare? So it's not enough to just say that's pretty rare. We can go further. We can say, how likely is this to have happened? And this is where we can use, if we go back to the home page and find our technology resources here in the middle, we can jump over and do the normal distribution where we enter one z-value. The z-value we want to enter is 2.63. Let's type it in. 2.63 for us. And here it is. What is the chance that we observe something that is this extreme or higher? So we're finding the area in that tail, and our chances are really not good. Oh my goodness. So the probability that our p hat is greater than or equal to 1.00, if we know that the population proportion is 50%, we came up with the probability of that is 0.0043. And this is a good chance to kind of refresh your memory. This is conditional probability. The condition that we are assuming is we're assuming that it was a standard deck of cards. So if it was a standard deck of cards, the chances that we would see something that is a z-score of 2.63, which means our p hat of 1 or higher, which we couldn't get higher than 1, but that's how we can write it down, is extremely small. Extremely small. This also gives a lot of weight to you coming back and saying, you know, I've got pretty strong evidence, Mr. Falstrom, that I think you were cheating. I think you weren't using a fair deck. Now again, you have to understand that if you make that type of a claim, you might be wrong. You're wrong about 43 times out of every 10,000. So we're not 100% sure, but we are so confident that we could come forward and make that claim. Now you saw me using a couple things as I was going through this. First off, let me jump back to this other page. This is when you get to page 14 of 23, you'll see the formula for standard deviation is here, and the formula for kind of checking ourselves is here, making sure we see enough of the right successes and failures. And that's where I want to bring that back to. We did a lot of work right there. However, what we didn't do is we never went through and checked to see whether we should actually be using a normal distribution. So we did seven coin flips with a 50% chance of success. And if you multiply that out, I get the number 3.5. So on average, we'd expect to see about 3.5 times we'd get a black card. And that's not 10. So even though we did all of that work, unfortunately, it's based on a model that we cannot use. And so by me working through that entire problem, what I want you to see is why you need to check the shape by checking the normal conditions before you start. So this is probably the most frustrating thing for students in this class, is they will do a lot of work and they will ignore the normal conditions. The normality condition is what you have to check in order to use a z-score, in order to use those applets. Okay? So I would have to go flip a coin a lot more. I'd have to draw a lot more cards in order to bring up my expectation so that the distribution fits a normal distribution. So super important, and there's another example of that as you go through. So make sure normality conditions, even though they seem to be the third thing down, they are the first thing that you should be checking. All right? Really super important as you go through there. So let's see here. There's another example given a little bit later, and the formula that's listed here is so similar to the z-score that we've seen before. It's just now saying statistic instead of our data value, but our data value comes from the sample, and so the sample, statistic, those two words go together. The parameter and population, those go together, and that's why you see p hat minus p divided by the standard error. So this formula is a good one. Again, I would probably jot this down on my note sheet to have that ready for the test, just so I don't have to keep flipping back and forth. Okay. So there's a nice example that goes through, and they found out that about 10% of 18 to 24-year-olds were in a community college. And if you randomly selected 100 people and you came up with 15%, well, that 15% is higher than what you would be expecting. And so now you want to be kind of saying, well, wait a minute, how often, how likely is it that we would see something like that? And they work through the entire problem very similar to what we just did. Okay, so there's another nice example for you to kind of look at. The last piece is really talking a little bit about how error plays a role in this. Remember, we might expect to have a little bit of error because our sample isn't perfect. And so let's take a look at this. This is part 20 of 23. So let's say that we grab a sample of 40 men and we find that 58% are overweight. And we know the data that says 68% of men are overweight. Again, the data is a little bit old, but we'll have to assume that for now. So if the real number is 68% for the population and we find 58%, how likely is it that we would have ended up with that much error? So what's the probability that our sample proportion will be an overestimate or an underestimate by more than 10%? Okay, let's go through it together. First things first, check the normality conditions. Seriously. So what does that mean? That means I need to take the n value, which is 40, because that's our sample is 40 men, multiply that 40 by the chance of success based on the population. Population amount was 68%. And when we do that, we end up with 27, which is more than 10, so that's good. Now check the opposite side. And so the opposite side, when I multiply, gives us 13. Again, it's more than 10, and that meets our expectations, so we can use normality in this case. Now we're going to find the z-score. Now, the reason we need a z-score is to turn that into a probability. So what we can do is very similar to what we did before. First, we need to find our standard error, and that is done here. We can use Desmos or any other type of calculator, but we come up with about 0.074 as our standard error. Now when we want the z-score, that's where we take our value, the 58% that we found, take the 68% that is the population parameter, and divide by the 0.074. Now because the sample was below, we should get a negative number, and that makes sense. But we could have also had an overestimate, so we could have had a 78. So if you would have put in a 78 in here and kept 68 for the population, what you'd end up with is a positive 1.35. So in a normal distribution, what we're looking at is if we want to go out about 1.35 above and 1.35 below, and we want to kind of find out how much is in this chunk. How much is in this chunk? These two pieces are kind of the chance that we're wrong by at least that much. So we go back, grab our fantastic tools that we have available to us in this applet, and we can type in 1.35, and I can enter 1.35 and notice that the portion above is 0.0885. I could also enter a negative and try it on the negative, and the portion below that is 0.0885. So now what I really know is that I end up with 0.885 really multiplied by 2, because there are two pieces that are exactly the same size. If you wanted to get like a really quick estimate, oops, I forgot a 0. I would put in just kind of round that to like 9% and just know that you're a little bit overestimating. And that gets you a really quick rule of thumb instead of maybe needing a calculator. So about 18% of the time we would expect to see a sample that's down here or up in that kind of same wedge. So that's how our error comes into play. Again, so it's okay. We have to accept that we're going to be off a little bit. Not every sample is going to be perfect. Samples have variability, and the fact that there's variability means we're not always going to be right on with the population. All right. So I hope this gives you a pretty good outlook on what we're doing. We are moving forward, definitely using probability, z numbers. Now we're bringing in the idea of how does this apply to sample proportions, and how can we bring it back to that population and kind of compare what we found. So pretty exciting stuff. I'm super excited about it, and I hope you are too. And I think this should wrap it up for Module 15. All right, off you go.